All right, so good day, everybody. My name is Ed Stehmeyer. I'm a general manager of projects and design with the South Carolina State Ports Authority. So you started off the webinar with bridges, you moved on to buildings, and now you've got marine structures. So there's definitely something here for everybody in this presentation today. The topic I'm going to present to you today on is the in-situ dynamic pile testing to realize wharf renovation savings. And hopefully, as we move forward, you'll be able to see what we're talking about here. So let me see. All right, so a brief presentation outline. I'll start off with an introduction, move through the project goals and existing site conditions, talk about the actual testing that we did, the subsequent results and analysis, and the interesting thing that a lot of people talk to us about, especially on this project, was the estimated construction savings, not only in dollars, but also time, and talk about construction successes, and then end up with some conclusions. So this is a photo of the Charleston Harbor. I'm not sure if y'all are familiar with Charleston, but we are located in the east coast of South Carolina. We have a number of facilities that we own and operate in the Charleston Harbor. The one that we're going to be focusing on today is on the right, the Wando Welch Terminal. So the Wando Welch Terminal is actually located in Mount Pleasant, South Carolina. So basically across the river from the Charleston Peninsula. It's over 250 acres. We've got ship-to-shore cranes on the dock. Actually, before the project started, we had 10. And as of now, we actually have 15. So we've been growing by leaps and bounds. Actually, part of my slides cut off. So the approximate capacity. So before we really started this project and a lot of the improvements that we made, the capacity was about 1.6 million TEUs. And around now, we've got a capacity of around 2.4 million TEUs. Normally, when I make these presentations, I always have a quiz question. What is a TEU? So a TEU stands for 20-foot equivalent unit. So anybody who's ever been dealing with the port industry and containers and stuff like that, there's standardized sizes. So they're either 20-foot long, 40-foot long, or 45 feet long. So a TEU is a 20-foot equivalent unit. So just a little bit of quiz knowledge for you today. So our project goals, when we started this out, this wasn't one thing. It was a sort of a collection of things that we saw in the industry that sort of drove us in this direction. Ships are getting faster. Ships are getting larger and larger at a very fast rate. So we had several different objectives, and we're only going to talk about a portion of it today. But we were looking at deepening the Charleston Harbor, which is underway now and should be done later this year, to minus 52 feet, mean lower low water. It's about a 7-foot deepening. In some areas, it may be more. We're also looking at servicing these larger vessels. In the bottom left corner, you'll see the CMA, CG, and Theodore Roosevelt. So that 20-foot equivalent box I was talking about, these ships can carry upwards of 15,000 TEUs of containers on the vessel. Whenever the Wando Welch Terminal was originally developed, it was suited for more like 4,000 or 5,000 TEU vessels. So that's a substantial increase in vessel size. As a result of that, we also have to increase our crane capacity. I'll talk in detail about that today and sort of how that resulted in the renovation that we're looking at. As a result of that, we got bigger ships coming in. We also have to increase our container storage capacity and throughput on the land side, and increase productivity through the gates and all that kind of stuff. We're going to skip over that today, but I want to sort of give you an idea of what we're looking at. So if we focus mostly on the ship-to-shore cranes, I'm not sure if y'all have ever seen this operation or not, but all the containers are stacked on the vessel itself, and we use ship-to-shore cranes to reach out, pick that container off of the vessel, bring it onto the dock, put it on a truck, and it goes into the yard. Whenever we started this project off in 2015, we had primarily 115-foot lift height cranes. So if you look off to the left, there's 115 feet in between the hook or the grappling hook where that crane actually connects to the container, all the way down to the top of the wharf deck. That's 115 feet. This is just showing, like I said, a typical condition of the Wando Wharf that we started with. Now, we knew with these larger vessels coming in that as they get larger, they not only go deeper, they also get taller. So we had to, through a pretty detailed study, we realized that we needed at a minimum 155-foot lift height, as opposed to the 115 that we originally had. Whenever you do that, you go to 155-foot lift height. That obviously causes a whole bunch of issues, like you heard in the bridge design example earlier. We had all kind of different loading increases, not only from just the crane being heavier, but also as you get taller, the wind forces also get bigger. So we had increased wheel loads and increased tie down loads. In South Carolina, on the East Coast, we obviously also have hurricanes to worry about. So as you get taller, the wind force gets taller, the wind force gets higher. Also increased our tie down loads for securing the crane to the dock during a hurricane. So we actually had, as a part of this project, we had 4 new cranes that we purchased and in service in between October 2016 and July of 2018. We also raised 4 of our existing cranes 40 feet each, and those were completed in November of 2018, just to give you an example of the outside investment that are going on besides what we're about to detail here. So our cranes also are interesting in the sense that when they come to us, they're actually lowered down. We have this is the Arthur Avenel Bridge in the Charleston Harbor. So as they come to us, they're actually lowered down, and they are brought to our site. You'll see it sort of in the middle of the picture there. They're brought on vessel. They're offloaded onto our wharf, and then they will look like this after a couple of months. You can see the height difference in between those two there. We showed it in one picture earlier, but this is definitely a visible change. Not only the nicer blue new paint job on the left, but also you can see the lift height in between the booms is definitely different, and that's the 40 feet that we've been talking about. Now let's look at the existing site conditions. Now we know kind of what we're dealing with as far as looking at ship-to-shore cranes and higher loads as that results. So we also had to deal with the fact that this is an active terminal. The wharf itself, berths 1 and 2, as you'll see in the green and blue, were built back in 1982. They were founded on 18-inch pre-stressed concrete piles with a pile cap and one-way reinforced concrete slab construction type. Berth 3 was built back in 1994. It was founded on 24-inch pre-stressed concrete piles and a 2-way reinforced concrete slab. And as I mentioned, the sizes of the vessels have been changing over time. I say it's berth 1, 2, and 3. Whenever these berths were originally constructed, it was suited for 4 ship parking spaces as opposed to 3. So the overall wharf length is 3,800 feet. So 4 parking spots there. You can imagine the size difference in the ships that are coming in now when we have to narrow it down to just 3 parking spots for the wharf. So this is, again, a wharf cross section. Let's talk about the existing site conditions. You've got, like I said, a marginal wharf where you've got an existing slope underneath this wharf. Again, it's pile supported. The existing slope itself had armor stone on it in certain areas, underlain by soft organic silty clays. And then the Cooper marl, which I'll talk about in more detail in just a second, is really our foundation layer that we're trying to get to with all of these piles. You can see also off to the left, we were authorized dredge depth of minus 52 feet. So there's a lot of work going on there to not only improve the topside structure, but also the berth and access channel outboard. So the Cooper marl formation, let's talk about that for a minute. It's a firm to stiff clay. It's like I mentioned, it's our typical bearing stratum for deep foundations in Charleston. Getting into details a little bit, it's an over-consolidated, highly plastic clay, or silt, if you want to sort of categorize it that way, with an over-consolidation ratio between 3 and 6. We have a very high undrained shear strength values. This is your SAT word for the day. That we're geologically classified as fossiliferous. Say that one 5 times fast. A fossiliferous limestone. We have the interesting thing about this is anytime you do a CPT sounding in our area, you can definitely tell where it is because you'll get a spike in the excess pore water pressures during the CPT soundings. What you're basically doing there is you're breaking the cementitious bonds or shearing the clay in that instance, and you get an increased pore water pressure as a result. For pile installation, it's a very nerve-wracking thing, and I'll show you why in just a minute. But the pile setup with time, you can actually get a 600 to 800% increase in the capacity whenever you look at the end of initial driving to final design conditions, if you will. So this is the good stuff. But again, I mentioned it's definitely, it can be sort of nerve-wracking to use this material in some instances. So as I mentioned, we're trying to do these renovations to an active terminal. we had to deal with a phased approach inside of the crane rails to do this testing. And I'll explain why we decided to do the testing in just a minute. But we have ship to shore cranes on crane rails that must stay active during the testing and construction. So we have two phases. Phase one, which is off to the left, that's in berth 3, where we will be testing the existing 24-inch pre-stressed concrete piles. We had a closure of 74 days of this small area, and I'll show you what that area looks like in just a minute. Phase 2, we worked in berth 1 on the 18-inch pre-stressed concrete piles that were used as a foundation there, and we had a shorter closure of 33 days in that area. And we gave the contractors approximately about 3,000 square feet up top on top of the wharf, as well as some waterside access where we had all the barges staged outside of our berths so it didn't impact vessels coming and going to the wharf. So let's look at berth 1 first. As I mentioned, this is a phased approach because we couldn't shut everything down or have contractors working on both sides at once because it actually shortens the length of your wharf if you do that. And we had all the barges staged outside. If you notice in the figure, the sort of the purple 50-foot by 120-foot barge staged outside of the wharf, as well as the berth itself. We gave them about a 60-foot wide by 50-foot area on top of the deck to work. And you'll see what that looks like in just a second. And again, this was closed for 33 days. This is just a topside view of what it looks like. It was wide open at the time of this photo, but in general, if we have operations going on, you've got trucks parked there or even containers or hatch covers put down in these areas. So anytime we were testing in this area, we were losing operational space. So the demolition extents, as you'll notice, the P2 and A5 off to the right are actually where the crane rails are. So we were actually in the middle of the wharf. And we tested 2 interior piles. You can see the hatched area there is what we ended up demolishing out to gain access to 2 18-inch pre-stressed concrete piles. So we tested 2 on either end. So if we look at berth 3, very similar situation. You have 50-foot by 60-foot work area. Same situation when it comes to the barge staging and whatnot, but the construction was different. So the actual work area closure time was different because of the reconstruction. So we're doing all this demolition to get to these piles, but we also have to do the reconstruction to get things back up and running. So looking at the demolition extents in berth 3, since this was a 2A slab, we ended up using a smaller demolition area around to get access to the piles, but we had to use steel strongbacks and W36 beams on top of the deck to spread the load out to adjacent piles and crane beams. So again, we couldn't take the ship to shore crane rails out of service. So we tested the interior piles, if you will. And I'll show you that in just a second in the section view. That's again why we had a longer closure time. And this one just because of the construction differences and the reconstruction duration. All right, so let's start taking the stuff apart. If we're looking at, this is berth 1. This is the 18-inch pre-stressed concrete piles with a pile cap and one-way slab construction. As you can see there, we tried to save as much rebar as possible because we're going to have to put it all back and reconstruct it. But to gain access to those piles, we had to do a lot of demolition. This is what the work area looked like from up top. So you've got a barge offshore of the wharf itself, but it gave them enough room to put a small excavator in there with a hoe ram to do the demolition, as well as the power packs and everything for the hydraulic hammer. So Cape Romaine contractors did this testing for us. In the construction, they used a J&M ICE 220 hydraulic hammer, which had a 3.5-foot stroke, 22 kip ram, which resulted in an energy of 77,000 foot-pounds capacity. So we did PDA testing using that hammer, and what we ended up finding was the data that you see in front of you. Basically, with the Cooper Marl, primarily, you've got usually in between like 80, it's like the 80-20 or 90-10 sort of split in between side friction and in bearing. And we were that sort of rule of thumb sort of held here as well. But we had a pretty substantial capacity confirmation, if you will, during this testing. As you can see in the lower right corner, we had a bearing capacity, ultimate bearing capacity that we mobilized of 677 kips and 642 kips in that 18-inch pile, which is good because we had lower capacities that were on the original design documents, which we'll talk about in just a minute. So that testing was really important. The other thing to note that we ended up using is that the upper left corner, the displacement versus load, that pile stiffness, the axial pile stiffness, was also something that we used in our analysis to really help us out later on, and I'll talk about that in just a minute. So similarly for berth 3, we used the same hammer and barge setup, and we also got to the top of those 24-inch pre-stressed concrete piles, and we're able to mobilize capacities in between 975 kips and just over 1,000 kips in each of those piles. Down the other end, you can see the same distribution of side friction and end bearing in those piles as well. So as I mentioned, we couldn't take the shift to shore crane rails out of service. So what we had to do is, since we picked the middle piles or something close to the middle, we ended up having to extrapolate, if you will, the capacities of new and existing piles underneath those shift to shore crane beams. So if you look off to the left, you'll see blue and green piles. Those will be the piles that actually resist the shift to shore crane loads. The crane rail above those piles was also ended up being reconstructed because of structural issues. But the foundation itself, we had to sort of extrapolate our test pile, which is the red in the middle, to the water side and land side situations. So we considered a number of different things, overburden. You can see the one on the land side has a lot more overburden over the stiff clay than the water side does. The marl embedment, we knew the marl embedment we had a good idea of the marl embedment from installation logs of these piles. So we could use that to sort of extrapolate the capacities for new piles. We also had to consider pile proximity. As you look at the water side, and I'll explain more in just a minute, but we had a lot of other piles around these, new ones that we're going to install, as well as existing piles. We had to consider that. And we also had some variation of the elevation of the actual marl along the length of the wharf. We had to consider that in all of our analyses. So what you'll see here is an allowable pile bearing resistance comparison in between sort of where we started in design and where we ended up as a result of testing. So in the upper table, you'll see that we had, for those 18-inch piles, the initial allowable bearing resistance based on information used in the initial design of the wharf, those piles, the allowable bearing resistance was only 160 kips. Similarly, for the 24-inch piles in berth 3, it was higher, but still not huge numbers here. If you look at the revised allowable pile bearing resistance range off to the side, and that range is because of the pile embedment changes as you go along the length of the wharf and the variation in the marl depth, you'll see some pretty substantial differences there. You got 50 to 78% increase, 73 to 96% increase, 83 to 119% increase. Similarly, for berth 3, we saw some pretty substantial resistance increases in between 450 and 600 kips as a result, going up 41% and 88% as a result of just this testing. So having done this testing, we had a very valuable tool in our hand to move forward in design. And I'll tell you more in detail about what that did for us in a second. But when I said this can be a very nerve-wracking material to deal with. If you look at the bottom portion of this slide, it says side note 1 day versus 14-day versus 21-day PDA restrikes for ongoing composite pile driving. So whenever we were actually doing this construction, we took note of this. And at the end of initial driving, just on this one pile, for instance, we had we had 4 blows per foot was where we stopped driving that pile. And as a structural engineer, it always makes me very nervous just about how low resistance that seems like. But we know through all this testing that resistance actually goes up with time. You can see that as a result. So the end of, if you look at the bottom number, for instance, this is the same pile, but basically a month later, we tested it at 7 days, and then we had to wait and test it at basically a month, which is another 21 days after the initial driving. You get a resistance at the base of 6 blows per 1 inch, and a pretty substantial increase in the capacity of the pile. And these are different size piles and whatnot, but wanted to show you that at the end of driving, the marl doesn't have that that really high end bearing resistance. It takes time for the clays to remold around it, but you do get that setup within 14 to 21 days that ends up getting you into the capacities that we tend to use. So what we did with this information, as I mentioned, is we were actually able to use the existing axial pile stiffnesses to our advantage, if you will, because before we didn't really know how stiff these piles were. We thought they were a lower capacity, but using those existing pile stiffnesses, we were able to sort of optimize where all the loads were going and get a better idea of what was actually going where. With that information, and oh, excuse me. So with that information, as well as the extrapolations, like I was talking about earlier, we were able to optimize our new production pile lengths, which, as you know, that's also a good bit of money there. If we're able to have a higher confidence in our numbers, we actually were able to help reduce some production pile lengths there. And just some rough numbers, we were able to reduce our waterside piles from initial design to final design by 40%. And same thing from the land side, we were able to reduce our number of piles there by 12%. That's just a total number of piles, not even looking at pile length. And burst 3 was really the winner from all this testing. Again, we were able to use the existing axial pile stiffness a little more effectively to get the load sharing done right. And our revised capacity said that we didn't need any new piles in this berth, even with the increased ship to shore crane loads. That was a really exciting day for us because we knew we had to do some local strengthening of the crane beam as a result of just the higher wheel loads, but to not have to drive any new piles in this berth was a substantial win for us. There's a substantial amount of reduction and demolition of the existing structure and the downtime there that we'll talk about in just a second. So again, if you look at the total number of piles in berth 1 and 2, so pre-testing, we were planning on needing 592 piles, and post-testing, we ended up with 361 with a 40% reduction, as I mentioned. And again, in berth 3, we were planning on over 336 new 24-inch pre-stressed concrete piles along those crane beams, and we ended up with 0. That was like I said, that was a very good day to receive that news. So just to give you a frame of reference, we had an estimated construction cost savings. We spent about $275,000 on the testing program. That's about 0.4% of our overall construction budget. And when I say budget, that's actually what we spent, the 0.4% number. And we ended up with what we're estimating is $9 million in construction savings. Most of that is the piles themselves, but also there's a lot of demolition that we did not have to do, particularly in berth 3. That this testing program saved us. And not only was it pure construction dollars, it was also it's a very hard number to quantify for our operations, but we originally estimated the project to be about a 32-month project. That's renovating from one end to the other of the wharf over those 3 berths, 3,800 feet. We believe we realized over a 6-month savings in having a berth offline. I'll show you that in just a second. There's a 19% reduction in just the construction duration. So just to give you sort of a timeline here, we started in September of 2015. We had to do different phases of construction because we couldn't shut the entire wharf down all at once. We had to keep doing business so we could spend money on construction. Phase 1 was only 600 feet. We finished that in May of 2016, and that 600 feet was very specific because we had those 2 new ship to shore cranes coming online. We brought those into that phase, and that's where they sat for a while they were being commissioned. We finished phase 2 in December of 2016, and as you can see, we sort of marched all the way down, getting 2 more cranes in March of 2018, and then by May of 2018, we were substantially complete with the entire length of wharf. As I mentioned, whenever we're doing this renovation, we essentially had to shut down a berth. So anytime you shut that down, that means the ship can't come in there. That means they can't bring in containers to the facility, and you're losing money every time you're down, every minute that you're down. So that construction savings, like I was talking about, that 6 months is really hard to quantify, but I can guarantee you it's more than we saved more than the $9 million we saved in pile testing or the pile cost that I mentioned earlier. So this is just showing you some construction photos of where we brought in the piles. We actually used composite piles whenever we went back. We did have some issues that we knew of from the 90s, early 90s construction of Berth 3 with the higher, 24-inch pre-stressed concrete piles bouncing a little bit in the stiff clay layer. So we actually used composite piles here. But with PDA testing and everything, for these production piles, we were able to confirm all of our assumptions that we had in the initial testing program. So we installed over 410 piles with a total length of over 40,000 linear feet of pile. So in concert with all that pile installation, we had a lot of other things going on. We had to replace bollards, do selected concrete demolition, rebar placement, concrete placement, and crane rail placement. We installed over 7,560 feet of 175 pound per yard crane rail. That's the largest Buy American compliant crane rail that's domestically available from one end to the other. So that was a pretty interesting part of the project as well. And then, as I mentioned, we were substantially complete in May of 2018. You can actually see in the middle there, those are two of our new, at the time, ship-to-shore cranes being developed. But that was a very interesting process to get this moving forward through that phase construction on an active terminal. Like I said, it was a really interesting project. But some of the things that we came up with here is that, what we showed here in this presentation was a dynamic pile testing of existing pre-stressed concrete piles founded in the Cooper Marl Foundation. The in-situ testing used to determine the as-built compressive capacity and stiffness of the piles for larger working loads and load sharing was very key here. We used both of those, not only just the actual capacity of the piles, but also the stiffness to really refine our design and save some money there. And as I mentioned, we had some minor operations disruption during those 33 days and 74 days areas whenever we're doing the pile testing, but it resulted in over $9 million in construction savings. And it's really hard to quantify this, but I can guarantee it's more than 9 million. But that 6 months of construction duration was 6 months of time that we were able to bring in containers through an active berth, and that was a very big win for us. So with that, I want to thank you for your attention and your time, and I want to also thank sort of co-authors on this study, Greg Canavan and Billy Camp with SNME.